answers you want repeated?
What is that?
Number 5 is 20.
Oh, I'm dumb. I thought that 2.3 million was the total blocks they used, but they were asking how many was 80%. I'm dumb.
No, they only used 80% of the ones that are available. Right. So the 2.3 million is 80% of the blocks that they had available. So they had available more blocks than they used, which makes sense. They certainly couldn't have used more blocks than they had available to use. Problems you want to go over? Number 2. Okay. The Pyramid of Cheops near Cairo contains 2,300,000 blocks of stone. The builders only used 80% of the available blocks. How many blocks were available? As we just said, this 2.3 million
What's the 80%?
is 80% of the blocks available. When they were building it, they used 2.3 million,
So
and that's 80% of what was available.
divide 80 over 100 by 80 over 100.
Yeah, but first let's simplify.
Oh, okay. 8 over, so 4 over 5?
Yeah, 4 over 5 times A is going to give us 2.3 million. Now what do I do?
Then you divide 4 over 5.
Yeah, I divide both sides by 4/5, or what can I do instead of dividing by 4/5? Yeah, I can multiply by 5/4 instead, multiply by the reciprocal. 2.3 million.
Well, isn't that what you're doing when you're dividing?
Yeah, it's the same thing either way.
Oh.
Times 5/4. What do I do now?
Multiply. Ridiculous. Oh, wait, you can, yeah.
You can simplify. I can divide this by 4. How can I tell that I can divide that number by 4? How do I tell whether I can divide something by 4? Not everything. 10 has a 0 at the end. Can't divide that by 4. Right, we look at the last 2 digits. If the last 2 digits are divisible evenly by 4, then the whole thing's divisible by 4. So since we've got 0, 0, that's going to work. All right, what's 2.3 million divided by 4? Well, how many times does 4 go into 2? How many does it go into 23?
5.
And how many left over? 4 goes into 30 how many times?
6. Yeah. No, 7.
7 times, and how many left over?
5.
2 left over. 4 goes into 20 how many times?
5.
Good morning, Ann. And then we can just do zeros the rest of the way. 575,000 times 5. Gives us. Please be on time for class. Please be on time for class. You need to be in the room when class starts. Do you have the homework? Homework, take it out so I can check it, please. We were just going over number 2. Number 2, like so many of these other problems, it's just a matter of setting it up correctly. Understanding the scenario here. If the pyramid has that many blocks in it, that's how many the builders used. But that was only 80% of what was available.
We do 9 and 10.
What are those 2? Not 27 and 30.
What was the answer to 2?
Oh, it's
It was 2.
It was 2.875 million.
That's cool.
Yep. That would have been.
All over you. Yeah.
You know what? You guys can. I recovered. I recovered. Okay, it's fine. It didn't happen this time. It has happened before, though. See, I made the mistake of walking through this corridor. Thank you. I intentionally set up the cord so that I don't have to walk over it while I'm teaching. But then I made the mistake. I should have gone around this way.
Get duct tape and put it right over the cord and tape it to the ground, the green one.
Yeah.
It's flat with the ground.
Yeah, I mean that would be a better solution. All right. Otherwise, you want to go over? Somebody asked about 9. 9 and 10. Okay, 9 and 10. We're simplifying radical expressions. 9. Read 9 for me, please.
6 radical 45 plus radical 185.
What do we have to do here to add these together? What should I be doing first?
Break it down. 6 radical 45.
So
How can we rewrite 6 radical 45?
6 times radical 9 times radical 5.
Right, 6 times radical 9 times radical 5, or what?
18 radical 5.
Yes, 18 radical 5, because what's radical 9?
3.
3. 3 times 6 is 18, and the radical 5 is still there. What about 180,000?
This is the one I was too late. I was too late.
Oh, wait, that's 100.
180,000.
It could be a perfect square root. That's
Okay, we've got an even number of zeros, so we can definitely take out a perfect square power of 10. What perfect square power of 10 can we get out of 180,000?
100,000.
100,000 has how many zeros in it?
Oh, wait.
Five.
You are.
First of all, you can't divide it by 100,000.
No.
You could get 100 out of it. What else could you get out of it? How many zeros does 1,000 have?
10,000.
So is that a perfect square?
No.
No.
10,000.
We can get 10,000 out of it. 10,000 has how many zeros? 4. So is that a perfect square? Yes.
Yo.
10,000. What happens what do we get? What's the other part going to be? Radical what? 18. Okay. So 10,000, what's the square root of that?
100.
100. What about square root of 18? What's that? Can we break that down anymore? 18, we could break it down to 9 and 2. So square root of 9 times square root of 2.
So 10 radical
3.
30.
So what are we going to have? We're going to have 18 radical 5 plus what?
30 radical 2.
30 radical 2. Because square root of 9 becomes 3. 3 times 10 is 30 times radical 2. What do I do next? I do it again.
You can add them. Because they don't have the same radical.
I can't add them because they don't have the same radical component. It's like they're not like terms. That's it. I'm done.
Wait. Were you supposed to put 100 or 10?
Oh, sorry, 100. You're right.
Oh, so it's 3.
Thank you. Yeah, 300 radical 2. Mea culpa.
I apologize.
My bad.
Oh, bro, you know we have a Spanish test?
Next one you want to go over?
Oh, he said.
Next one to go over. You guys want to do 10 also?
Oh.
Ashton, yes, you want to do 10?
I mean, yeah.
Ashton, stop talking to him. I'm speaking to you. Thank you. Now stop talking to him. Number 10. Ashton, read number 10 aloud for me, please.
Two radical 8 minus 3 radical 30.
Okay. What do we need to do here?
Break both down.
Break them down. What's 2 radical 8 going to become?
4 radical 2, and then the radical 4 can be 2.
Right. So we get 4 radical 2.
Yeah. And
And then what happens with 3 radical 32?
You can do 16 and 2.
Yeah, 16 and 2 is going to be the way to do it. 16
Yeah.
and
16
2.
will turn to 4.
Yep.
That would be minus 12 radical 2.
Okay, now what do I do?
Negative 8 radical.
Right, since these are the same type of thing, over here I've got 4 radical 2's, and over here I've got 12 of them. If I subtract 12 from 4, I get,
Negative 8.
I've got negative 8 of them.
Ah!
Can you say the answer for 13?
Wait a minute, wait. Oh, no.
13, only B is irrational. The rest are rational. Notice,
Oh, I put integers for 8.
so, but the question asks whether they're rational or irrational.
I thought A was the only rational one.
Okay, so what does it mean for a number to be rational?
That it's
Q.
Not, it's not
A rational
decimal or
number
fraction.
can what?
I thought it was.
No, that's an integer. An integer is a number that doesn't have any decimal or fractional part.
Expressed as a fraction of 2 integers.
Right.
1
Oh.
half, 3/10, and negative 2/3.
Right. A rational number can be expressed as a fraction. Negative 4. How could we write that as a fraction?
Negative 4/1.
Right. What about pi? How do we express that as a fraction?
Oh, I don't know.
Okay, but Yeah, but pi doesn't count here because it's not an integer. Yeah, it's irrational. 22/7, how do we express that as a fraction? 22/7. What about 8.3 repeating? Why is that one rational? What does the line over the 3 mean? That it keeps repeating that 3 forever. It's 8.333333333 forever. Repeating decimals are rational. You can express them as fractions. If it's a repeating decimal, you can express it as a fraction. 0.3 repeating is what as a fraction?
0.3, no.
It's not 3/10. 0.3 is 3/10.
I think it's just.
But 0.3333,
I think it's 8/3 with the line over it.
What?
Yeah.
How'd you get 8?
yeah, where's that 8 coming from? First of all, 8/3 is greater than 1. This is definitely less than 1. Anyone? This one you should know.
That's 0.3.
This one you should know. 0.3 repeating is 1/3.
Why do that?
I don't know.
Why did you say it?
Because, oh yeah, you had that 3 times.
I mean, I at one point in history knew this.
Oh, well that's different.
Wait, so if I put, never mind.
So that one, so D is rational. But B is irrational.
Yes.
Because that decimal in pi doesn't repeat and goes on forever. Next.
Ooh.
How did 6, 7, and 8 go?
6, 7, and 8.
You said the answer now? Oh yeah, they
Yeah.
went, they got it.
Yeah, they're pretty good for me.
You say
He said them though? The answer? I'm pretty sure now.
No, I already read them off. Actually, you were on time today, so yeah, I'll read them off. All right, 6, 7, and 8. Oh, 6.
The benefits of being constant.
It's true. 6 is shh. You just asked for these answers. Please listen to them. 6 is 3, 1. 7 is 2, 1, and 8 is 4, 3. 6 is easy because the first equation has plus y and the second one has minus y. So we can just add them as they are, and we get what? When you add those two equations together, what do you get?
You got 2x equals 6.
2x equals 6, right. And then from there you get x is 3, and then you plug it in, you get y. 7, how do we do 7? How can we do elimination with 7? 2x plus 3y equals 7, and 2x minus y equals 3.
Yes.
How can we do elimination there?
Eliminate
Did you get this one right?
7?
I got it
Yeah.
wrong. I was confused.
Okay, what did you do to get it right?
Oh, I just added.
Okay, let's do number 7. We've got,
Three.
adding is not really going to help you here. 7. Looks like this. We got a system of equations. Wow, that is a really terrible code brackets.
I think I know how to do
2x
Yes.
plus 3y equals 7, and 2x minus y, is 3. What do I do here?
You multiply the top by 1, the bottom equation by 3.
We could do that. We could multiply this bottom equation by 3 and then add them together because then we'll have positive 3y, negative 3y. But here's something a little easier we can do. Instead of adding the equations, why don't we subtract them? Remember, I'm always allowed to subtract something equal from both sides. Please don't do that. The thing that you're currently doing. Please undo that and don't do that. Why don't we subtract them?
X will cancel.
What do I get? 2x minus 2x is what?
0.
0. What about 3y minus negative y?
2y.
No, minus negative y.
Oh,
4y.
Negative
Right. 0 plus 4y equals what?
10.
No.
4.
Yes, equals 4. I can subtract the equations also. Please put the sweatshirts away. Don't look at him. Look at the sweatshirt that you have out in front of you. Please put it away.
Oh, shit.
Thank you. At this point, then, we get y equals 1. We don't have to add the two equations. We could subtract them. That rule where we're always allowed to add the same thing to both sides of an equation means that we can also subtract the same thing from both sides of an equation.
So after that, how do you find x?
So how do we find x? Then we just take either one of these equations and we plug in y. 2x minus 1 is 3, or we could say 2x plus 3 times 3 is 7. Either one of those. So we get 2x is 4, x is 2. Or if you do this one, 2x plus 9 is 7. Wait a minute. What went wrong here?
Is it
Oh, sorry,
y?
this one.
Yeah, y equals 1, right? In the parentheses, you put 3.
Yeah, that's what it did wrong. Thank you. Yeah, 2x plus 3 is 7, 2x is 4, and x is 2.
Alright.
Once you get the value for one variable, you just plug it into either equation, and then you can solve for the other variable. 8 is the trickiest of these three. What do you have to do with 8?
Time about one.
Times what by 1 and 2?
Bottom line, 2.
The top and the bottom what? Please use nouns. Make it clear for people what you're talking about.
Multiply the whole top by 1.
The whole top equation, that would be a noun, is equation, that's a noun, yes. Right, so here, notice we've got minus 4y on top and plus 2y on the bottom. Before we add them, another thing I'm allowed to do to equations anytime is in addition to adding the same thing to both sides, I can multiply both sides by the same thing. Yes? So I can rephrase this second equation. So the first one I'm going to leave as is. The second one I'm going to multiply both sides by 2. So what is the first side going to become?
Wait, what did you say?
Oh, if you use 36 equals 36.
Right, I'm asking about the
4x plus 4y equals 36.
4x plus 4y equals 36. Before I add them together, I can multiply one or both of the equations by some other number on both sides. I can manipulate them twice if I want.
Wait, so you multiply negative 4y.
No, the first equation I left the same.
Oh.
The second equation, I multiplied both sides by 2. Why did I do that? Because I see I've got a negative 4y here, and I've got a positive 2y here. So I could have done that to solve it. Then I'd get 6x equals 32. X is what?
4. Wait, I don't know.
It's gonna be okay. We'll get through
No.
the first time together. Oh,
No, wait. What am I wrong here?
6, 12, 18, 24.
Oh,
6. 6. Oh,
2x minus 4y is negative 4. 3x plus 2y. Oh, it's 3x. Sorry, 6x. 8x is 32. X is 4. And then we can solve for the other one. Alternatively, what else could we have done to this? Yeah, that's really the best thing to do this equation.
I was about to say when it was 2x that you
Yeah, we could have just subtracted.
Everybody thinks they're not.
I'm getting you drinking water.
Yeah.
stop hungry.
Okay, other ones you want to go over? Remember, you guys have a test tomorrow.
Oh, yeah.
What's your last
Shh, quiet. What was that?
You're supposed to know good.
Well, so if you look at number 8,
Sure.
you can do anything that you want to these equations. The question is just shh. And pretty much within the rules, as long as you're adding the same thing to both sides of an equation or multiplying both sides by the same thing. What you're trying to look for is ways that you can get rid of one of the variables. So if we look at the first equation, the first set, number 6, we see the first one has plus y and the other one has minus y. So if we just add these two equations together, the plus y and the minus y are going to cancel out. We're going to eliminate y. If we look at the second one, we notice they each have 2x. So an easy way to get rid of one of the variables, x, would be to subtract them. If we look at the third one, 8, we see there isn't an easy way there. 2x and 3x, negative 4y and positive 2y. However, we see we've got negative 4y in the first one and positive 2y in the second one. Well, if we could somehow turn 2y into 4y, then we'd be able to eliminate. And what manipulations do I have to do to make that happen? It might be as easy as adding the two equations. It might be a little bit more tricky where you have to subtract the two equations. It might be a little more tricky where you have to multiply both sides of one of the equations by something first and then add or subtract them. And it could be, the most difficult thing is if you have to multiply both equations. So for example, if you wanted to eliminate x in number 8, what we could have done alternatively is we could have done this. We could have multiplied the top equation by 3, and we would have gotten 6x minus 12y equals negative 12. And we could have multiplied the bottom equation by 2, 6x plus 4y equals 36. And then subtracted the equation. So we get 0 plus negative 16y equals negative 48.
Oh.
We could have done that. We could have multiplied both equations by something. Notice I multiplied the top one by 3, so I'd get 6x, and the bottom one by 2 on both sides, so I'd get 6x there. Then I'd subtract them. You want to manipulate the equations so that in one equation and in the other equation, one of your variables has either the same coefficient or opposite coefficient. So either you have 6 and negative 6, 6x and negative 6x, or you have 6x and 6x. Because if they're the same, you can just subtract the equation instead of adding them.
Wait, so you multiply by whatever number 2x, like 2x,
Right, so here if I want to eliminate x,
you would, oh.
if I want to get these the same coefficient, 2 and 3, I can multiply them both up to what? 6. That's the least common multiple of 2 and 3. So I multiply both of them up to 6. So this equation, I got to multiply the entire both sides by 3. So it becomes 6x minus 12y equals negative 12. To get this guy up to 6, I'm going to have to multiply the whole thing by 2. So we get 6x plus 4y equals 36.
60 plus 3, right? Wait.
So it's 4.
Oh, 4, 15, 3.
No, sorry, it's 3. Yeah, you're right. You could also, if you got this on a test and you really wanted to, if you want to use substitution for this, go ahead. Yeah, go ahead. We don't need to know about it. Just go.
Sorry, it was an accident.
Yeah, that was not bad.
Yes. Hold on. Say it again. Right, if it can be expressed as a fraction. Repeating decimals, if you see a repeating decimals can always be expressed as a fraction. Non-repeating decimals, things with non-repeating decimals are the only things that are not rational. So square roots of non-perfect squares, things like pi and other things that we use Greek letters for usually.
17.73364.
No, because that ends. If it's got a non-repeating decimal that goes on forever, then it's irrational. But otherwise, if the decimal ends, we could just take that decimal, what's after the decimal point, and put it over a power of 10. That's how decimals work, is that each place represents a fraction over some power of 10.
Okay.
Okay, next up, from the homework. Anybody? Test tomorrow will cover up to and including lesson 64.
So no homework tonight?
No written homework, but you should be studying.
Woohoo! I don't have to study.
This is your last call, otherwise we're going to do 68.
Are there any, wait, why would we do that?
Because we have time to.
Or why would we?
Because I'm asking you guys if you want to review, and you haven't expressed any interest.
Wait, no, I'm sorry, I mean, what is it called?
Well, you're thinking about science.
No, I'm not, I'm thinking about what is it
Give me an example.
called?
Or like, talk to me about it. What happens? This type of equation that you want to go over.
Percent. Yeah.
Percent. Okay, so like, you mean like number 2. Yes? Okay, so that'd be lesson 58. Yes, I think that's an excellent thing to go over because we've had some issues with that. So let's just go back to lesson 58. Turn to page 237. Let's do the practice problems here. Let's do practice A and C on page 237. We'll do those two. We'll do those together. 237.
Oh,
That's lesson 58. We'll do practice A and C on there. Remember the practice problems, the answers are all in the back of the book, so you can go and you can do this on your own if you want and check that you got them right. All right, someone read number A for me, please.
Oh,
number A?
Yeah, number A. Number A. Whatever. Problem A. Practice problem A.
where am I at?
I don't know, but you were out, so you're probably not on the right
Lee
page.
and Faye have 32 bagatelles.
Mhm.
If they began with 160 bagatelles, what percent of their original number would be?
Yes.
You still wrong.
How do we set this up, this equation?
102.
We're page 237, Isaiah. Page 237.
Oh, I thought it was right.
They have 32 bagatelles left. If they began with 160, what percent of the original number remains? How do we set up the equation here?
Oh,
So they collected 40, so it would be 40 equal.
What?
Oh, wait, no, that's the wrong one.
We're looking at A. What's the question here?
What
and
percent,
they have 32.
No. The question is,
what percent of the original number remains?
what percent of the original number remains? What percent of the original number remains? Start translating this into an equation.
What percent? So, W over 100.
Yeah, variable, whatever you want to use, over 100
Times
times of
the original number is 32.
remains. And how many remain?
30.
How many remain, Matthew?
There are.
Look at the problem. It's there in black and white on page 237. How many remain?
Black and white, what are you talking about? I'm not black.
You're not on the right page.
I am on the right page. What are you talking about?
160.
I'm on the right page.
30.
Oh, yeah, no, my bad. Sorry.
How many remain?
33.
Thank you, 32.
Rectangle. Rectangle.
Once I get to this point, somebody please walk me through how I solve it from here.
Okay, I got you.
160x over 100, which you can simplify to
10 over 60.
8 over 5
8 over 5
equals
Yeah.
32.
equals 32.
And then you
No, I didn't
multiply
cut.
You do cos
32 over 1
Isaiah,
times
cut.
5 over 8.
Yeah.
Bro, I can't shut up.
Dude, I couldn't.
And then
Dude.
you can do 4 and 1, and you get 20.
Everybody follow along with that?
No, because I think it was talking, bro.
You're welcome.
What's your problem?
Exactly, bro. No problem.
Yes, the one I'm looking at, you.
I have no idea.
Bro.
They have no idea what I was talking about because you were talking while he was going through the problem. This is the part of the trips guys up to setting it up. What percent of the original number remains? What percent of, we know the original number is 160, remains. And how many remain? 32. Okay. Simplify this to 160x over 100. We can rewrite as 8 over 5 times x. We multiply both sides by 5/8. Cancel that out. 32 times 5/8 gives us 20. Viginti.
What's
up?
You know, Ashton broke the desk yesterday?
Oh yeah, actually.
He broke Mr. Stroot's desk.
No, the one in here.
No, all the desks are Mr. Stroot's.
Legally binded in.
Sorry?
He broke this one.
All right, please have a seat. Please have a seat. We got to do one more. One more. Shh. Great. Bring your stuff over there then. It's fine. Great, if you want to sit there. C, somebody read to me, please. Read C.
What are you doing?
Yeah.
Sit down.
I was not even-
Don't say my bad, which implies that it was some sort of unintentional mistake.
You took my
Oh, I did not.
When you got up deliberately and went over and messed with his stuff or whatever.
No, I had.
Shh. No, I don't want to hear excuses. I just want you to stop. Like, we're doing C. I'm going to make both of you move if you don't stop.
Dang.
You took my phone.
Okay, you sit there, you sit there. Now, practice C. Somebody read practice C for me, please. Somebody read practice C for me. Okay, moving on to lesson 68.
Chris and Chad collected 40 items. When they added Kathy's items, their total increased by 150%. What was their new total after Kathy's items were added?
Okay, now this one's a little bit trickier because here we aren't given a sentence that we can so easily translate into an equation. We're going to have to set up the equation ourselves. I'm going to ask you to leave if you can't stop moving my stuff around and making noises. So how are we going to set up the equation here? They collected 40 items, they added Kathy's, and their total increased by 150%. Now we want to know what? What's the problem looking for?
What was their new total?
I'm going to ask you to leave next time that you say something like that.
Their new
Okay,
total
please go stand outside. Please go stand outside. Please go stand outside.
How much the number, like how much they have after they added Kathy?
Right, we want the new total. So where did they start with?
40,
They started with 40, and then they, how much?
150%.
150%. So what? Express this as a sentence here, this equation for me. So 40, that's fine. You can talk about 150% of some number. But what do we, no. What is 100%? What does that sentence say about 150%? Their total what? Increased by, it increased by 150%. So what percent of the original items they have now? They have 250% now. If it increased by 50%, then they'd have 150%. 100% of what they started with plus 50% more. But they have 150% plus, sorry, they have 100% plus 150%.
Wait, so if 100% of the number is 40, they added 150.
Right.
So if you add another 100, it would be 80, and then half of 100 will be like 100, right?
So you could estimate it that way. But so we're talking about we need what percent of their original items? 250%. And how many is their original? That's the new total. The new total is 250% of what they started with. Please go stand. Go stand on the table.
It's shocking,
Watch your language. At this point, someone walk me through the arithmetic.
25 wait, over 1. You get 100. Wait, it was
Yeah.
actually 100?
It is actually 100.
Oh.
But notice you can, we know we're increasing it by 150%. If you increase by 100%, it doubles to 80. And then it increased by another 50% of that, so by another half, which is 20, so you get to 100. So here, this one, you could do in your head without too much difficulty. But you have to be careful. If some number increases by 150%, that means we're adding 150% on top of the 100% that they started with. Like if we get a 25% discount, that means that the price, 100% of the price decreased by 25%. And so now how much of the price do you still pay? 75% if there's a 25% discount.
Wait, so what if we got one of the problems on the test and we did our heck, we just put X was 100 or we have to solve it?
So generally speaking, with not showing work for problems, if it's sort of like this where it's reasonable that you could have done it in your head, I'll give you credit if the answer is right. The problem is if your answer is not right, I won't give you any partial credit. You didn't show any work.
So you get -4.
So you lose 4 probably, yeah. Because as far as I know, you just wrote some random number if it's not right. If it's right, I'll give you credit for it. But I recommend you show your work. But that's the big thing, and we ran into that with the test from last week, where when we're increasing by a certain percent or decreasing, we have to start at 100% and then adjust from there.
Oh, number 6, oh, Tom said 64.
64, you said?
Yes.
Tom said 64, that's page 263, number 6. Okay, x minus 2 is less than or equal to negative 1. Yes, that's the problem? Okay, we're graphing x minus 2, is not less than negative 1. And the domain is our real numbers. When the domain is real numbers, you can just ignore that. Because the real numbers are any numbers that we can put on the number line. So that's not going to affect our number lines at all. X minus 2 is not equal than, is not less than negative 1. What's a better way to write that?
X is not less than 1.
X is, how'd you get that?
Add 2 on both sides.
Right, just like with an equation, we can add, we're always allowed to add the same thing to both sides. We can do that with an inequality also. So here we have an inequality, that's fine, we can add the same thing to both sides. X is not less than 1. What's another way to write x is not less than 1?
X is greater than
Or
or equal to.
equal to. Greater than 1 is not less than 1, but equal to 1 is also a solution to that.
What if you put just
Look like this. But be careful, when it's not, when it says not something, all the other things are possible. So if it's not less than, greater than is a possibility, so is equal. You could have something like this. You could have x is not less than or equal to 1. What would that be? X is what?
not X is not less. X is greater.
Right, that would be x is greater than 1. Because there we say equal is not a possibility. Okay, there's always an equal. So here, this eliminates one of those 3 options, so there are 2 left. This eliminates 2 of the 3 options, so there's only 1 left. It's called the trichotomy axiom. Talked about that earlier in the year. Any 2 numbers are either equal or one of them is greater than the other one. Right, if it were integers, then we would start here. We'd have a dot on the 1, we'd have a dot on the 2, we'd have a dot on the 3, and so forth. Because if it's integers, then anything between the integers is not a possible solution if the domain were our integers. They're only ever going to give you, they're never going to ask you, tell you rational numbers for this one, because if it's rational numbers, you're going to have all sorts of weird holes in between those. And you just can't, you can't actually depict that on the number line. There's probably some really interesting stuff out there about the rational, irrational numbers that are distributed. So they'll only ever say things like your domain is integers, your domain, well, real is obviously integers, that's your natural numbers. They might say whole numbers, they might say negative integers. Anything up to and including 64. I will be available for at least some time after school today. I'm not going to be staying super late. If you have test corrections, please get them to me by the end of the day today, and we'll have our test tomorrow.
How do you do 12 again? I forgot.
From 64?
Yeah.
Number 12?
Yeah.
So you just have to know about the relationship between those 2 things. What does that curved C thing mean?
They're like
Subsets, right.
Yeah.
So natural numbers, is that a subset of all, or does that fit within whole numbers? Natural numbers
0, 1, 2, 3, 4.
are two, 3. Natural numbers are our positive integers. Whole numbers are non-negative integers. They start with 0. So,
They're not.
is it true that the natural numbers are a subset of the whole numbers? Is that true?
Yes.
Yes, because all the natural numbers are part of the whole number set.
Oh, I thought it said like you have to have a 0. It has to like match like the first few numbers.
So no, it's not about the numbers matching. It has to do with whether all the things that are in here are also in this guy.
Oh.
Think of this like a less than sign. Does this fit inside of this guy? The answer is yes, because 1 is in there, 2 is in there, 3 is in there. We can keep going forever. What's not true, it's not true that W is a subset of N. W does not fit inside of N. So make sure these are the two that people mess up the most, are natural numbers. Natural numbers are like things you might see in nature. How many goats you might see. You can't see 0 goats. But you can't see 0 goats. Because if you see 0 goats, then you're not seeing goats.
Exactly.
Whoa, that's deep, man. This is, yeah, maybe, but probably not some interesting things you can say philosophically about that. Whole numbers, though, include 0 as a whole.
Like a
Whole,
has
without
a hole.
0 has a hole in it, so it's in the whole numbers. Otherwise, for the most part, these aren't too hard to mix up. But they always.
The things are so creepy.
And then you've got your rational numbers. Oh, sorry, your integers come next. And then the rational numbers, and then your real numbers. What things are creepy?
Those things that you said.
What things?
The nesting.
The nesting dolls? Oh. No.
They do like one of the varieties that you get to.
Yes.
My brother's birthday was last week.
Oh, yeah?
Yeah.
Nice.
He's coming here next week for kindergarten.
Excellent.
He's a bad child.
Where's he going that's open?
He doesn't feel it.
No, for his
Oh.
classes.
You know the shopping center where Chuck E. Cheese is, like Montreal?
Really?
Yeah.
All right. We're done. We're out of time. You can come talk to me after.